Welcome back to Applied Algebra and Trigonometry. Today we're going to talk about simplifying expressions with integer exponents. Earlier in the course, we went over the rules of exponents. We're now going to expand on all of those rules, so take a look at them, pause if you need to, refresh your memory. To differentiate between the rules and the examples, today I'm going to use Roman numerals to indicate the example problems. So, we will start with y to the ninth times y to the negative 2. According to our first rule of exponents, I can add those exponents, which gives me y to the 7th, or I could rewrite y to the negative 2 using rule number 8, and then multiply. Let's see what that looks like. Now I have a quotient, and in this quotient, the numerator has the larger power. So I'm going to use this rule. I get to the same place, it's just a different route. Maybe you like the scenic route. Let's take a look at example number 2. Note that example 2 is not this, and it's not this, but it is this. Only the x is raised to the 0th power. Therefore, what we have is negative 3 times 1 because of rule number 7. So negative 3 is our answer. With example number 3, we get to combine rule number 2, rule number 3, and rule number 7. As I read this fraction, I come first to f, so let's deal with the f's first. The larger exponent of f is in the denominator, so my f will be in the denominator. And I will do 2 minus 1, because there's an understood exponent of 1 above the f in the numerator. G has a larger exponent in the numerator, so that's where my g will land. And then I have h to the 0th power in the denominator, which is, of course, 1. So my answer is g cubed over f. Here's example 4. Note that the squared term in the numerator means everything in the parentheses is being multiplied by itself. So we could rewrite this as x cubed y to the negative 5th times x cubed y to the negative 5th. But we have a rule of exponents that will help us with this, number 5. Because of rule 5, we can multiply our exponents within the parentheses to give us x to the 6th, y to the minus 10th. At this point, you can use rule number 8 to convert that y to the negative 10th to a y to the 10th in the denominator of our fraction. Now, note that the bases are different here, x and y, so we cannot do any canceling. Those exponents are not going to change. That's our final answer. But I'm going to move that answer over because I want to point out something. Note that inside the parentheses, we have multiplication. We do not have two terms separated by, in this case, subtraction, or it could be addition. In either case, you cannot go ahead and multiply 2 by the existing exponents. This just will not work, and I'll show you why. Remember I told you before that the squared term means that you are multiplying everything inside the parentheses times everything inside the parentheses, which results in this trinomial. Let's see how that compares to x to the 6th minus y to the negative 10th. It can be seen by this line that these two are not equal. But I went ahead and took it one step further to absolutely show that you don't get the same result. So this rule only works if there's multiplication within the parentheses, not addition, not subtraction. You must have only one term in the parentheses that you're raising to a power. But could you have done it in a different order? Yes. You could have first gotten rid of the negative exponent. And often that's what I do actually, because I prefer to get rid of the negative exponents and then do everything else. So if you had done it that way, your y to the negative 5 would have been forced to the bottom with the exponent positive. And then, according to rule number 6, you could have multiplied the exponents. Same destination. By the way, I'm saying root, R-O-U-T-E, not R-O-O-T, as in roots and radicals. If it helps and you ask me to, I could say it route in my native dialect. I'm going to assume that you no longer need to see those rules of exponents constantly, and also I need some more room, but you can always rewind, go back and look at them, or better yet, check your notes. Let's take a moment and think about another concept. X to the negative 6th becomes 1 over x to the positive 6th. But what happens if you have x to the negative 6th already in the denominator? Well, let's rewrite that as well. That would be equal to 1 over x to the 6th. So we have a complex fraction. But we know how to work with that and how to evaluate that. That's just the numerator times the reciprocal of the denominator, which puts x to the 6th in the numerator, although we usually write it just like this. So look at what's happened. In our first case, where we had x to the negative 6th, that negative exponent drove the base to the denominator and became positive. When our negative exponent was already in the denominator, it in effect drove the base to the numerator with a now positive exponent. And that's how we can think of it. If you have a negative exponent, you will be moving that base to the opposite position, whether it's from the numerator to the denominator or from the denominator to the numerator. Another thing to consider before we get back to our examples is that if you have a fraction and it is raised to a negative exponent, that drives whatever is inside the parentheses to the denominator with a positive exponent, in this case positive 2. And if I go ahead and square 1/3, I get 1/9 still in the denominator. Now what I have here is 1 divided by 1/9, which is the same thing as multiplying by the reciprocal to give me 9 over 1. And I'm going to leave it in that form because here's what I want you to see. 1 over 1/9 is equal to 9 over 1. So 1/3 to the negative 2 equals 3 squared. Being able to recognize this connection can help you more clearly see the steps of solution you should follow. But if this is still a little hazy for you, it'll get better with practice, number 1. But number 2, you can always go through the individual steps to get where you're going. You will just be taking the scenic route. Since I like to get rid of negative exponents first, I'm going to do that on the left-hand side. Then I will work the problem, simplify this expression a different way. In the aside that I wrote in gray, I showed you that 5 over x, all raised to the negative 3rd power, can be reinterpreted as x over 5 to the positive 3rd power. And then we can multiply all the exponents within the parentheses by that 3 that is external to the parentheses. Meanwhile, I can use the same rule of exponents to make the quantity xy squared equal x squared times y squared, and then that will be multiplied by x cubed over 5 cubed. Okay, and I can put my x squared y squared over 1, since I'm going to be multiplying that by a fraction. And when I multiply x squared times x cubed, I'm going to get x to the 5th. I'll have that multiplied by y squared. And on the bottom, I'll have 5 to the 3rd, which is 125. And I'm done. Or I could deal with this in this fashion. I could make my second factor there look like this. just bringing the -3 exponent within the parentheses by multiplying it by the exponents of 1 that exists there. Let's rewrite our xy squared as x squared y squared, and then let's deal with the negative exponents. This is like 1 over 5 and 1 over x cubed, or, as I already mentioned, those negative exponents can drive the base to the opposite position. The 5 negative to the negative third becomes 5 to the third in the denominator, and the x to the negative third that was in the denominator moves to the numerator as x to the positive 3. Now I can do my multiplication of fractions. X to the 5th y squared over 125. They are equal. Either method is equally acceptable. Moving on to example 6. I reinterpret our first term as 2 over t squared, getting rid of the negative exponent. In the second term, I'm going to get rid of the negative exponent, leaving the t plus 1 in the numerator. Now, you can see from this why I put that little hook on my t, because my addition sign there almost looks like an F or a T. Let me fix that. There's the wonder of video editing software. But that won't help me with the fact that I do not have a common denominator. My least common denominator here is t squared, so I have to find a fraction equivalent to t plus 1 over t with a denominator of t squared, and that would be t times t plus 1. I have to multiply by t in the numerator and in the denominator to find that equivalent fraction. So I have 2 over t squared plus, wait a minute, let's go ahead and distribute the t over here to get t squared plus t over t squared. So let me bring that over here, t squared plus t over t squared. And what does that equal when you add those together? T squared plus t plus 2 over t squared. Might be tempting to cancel the t squareds, but we cannot. There are grouping symbols around those additions. We have 3 terms. We do not have anything that we can cancel. So we're done. And we're moving on to example 7. There's nothing new here. We're just reapplying those same rules of exponents. This problem is quite similar to the previous problem in that we have to find a common denominator, which would be b squared as the least common denominator, and write an equivalent fraction for the first of our 2 fractions, and then subtract. Do not say 3 minus 3 is 0. We have 2 different terms here. We have a 3b and we have a minus 3. They are not like terms. They cannot be combined, and this is all over b squared. For example 8, I'd like to show you what a difference a set of parentheses makes. By placing parentheses around 3 times b, I drive that entire product to the denominator. It becomes 1 over 3b, and then I have minus 3 over b squared. I did not add any parentheses there, so the term is the same as it was in our previous example. What has changed is our LCD. It is now equal to 3b squared. So for my first term, I'm going to have to multiply 3b by b to get b squared, so I have to multiply the numerator by b. And then for the second term, if my LCD is 3b squared, which it is, I have to multiply the numerator and the denominator by 3, so 3 times 3 is 9, and when I combine those two, I get this. And I'm done. I have a very different result with these parentheses than I did without them. One final example. All right, pause the video and give this a try. As you can see, I have once again chosen to get rid of my negative exponents first. And now I'm going to deal with everything else. So I have 1/5. I'm going to leave that alone right now because I have those parentheses. I'm going to deal with what's in the parentheses first. My 1 over 3 squared is the same as 1/9. Then I have 4 minus 1/2. Well, that's equal to 3.5. But let's go ahead and change it to fractional form. So 4 becomes 8 over 2, because I need a common denominator of 1/2. So I have 8 over 2 minus 1/2 equals 7 over 2. That's my denominator. And now I have 1/5 times this division, which is the same as 1/9 times the reciprocal of the divisor. So I have 2 over, let's see, 63 times 5, whoa, 315. I'm done. So, when are you finished simplifying ratios or fractions with integer exponents? You are finished when there is no common factor in the numerator and the denominator that you can get rid of. So just like dealing with normal fractions. But since we're dealing with exponents now, integer exponents, you cannot declare that you're finished until you've gotten rid of all of the negative exponents. And now I declare I'm finished with this lesson, and I will see you in class.